All right, so it's my pleasure to introduce our next speaker, Vyacheslav Futorny from SUSTEC. He will give a talk about smooth representations of affine algebras. Slava, please.
Thank you very much, Koda, for the introduction, and thank you very much, the organizers, for organizing this wonderful event and for the invitation. So this is my second time in BIMSA. It's a great pleasure. So let me set up the notations first. G will be simple, complex finite dimensional Lie algebra. And our basic toy example will be GSL2. The affinization that I will denote by G hat. For simplicity, I will work with untwisted. So this is affine Lie algebra. And for simplicity, I will assume that G hat is untwisted one. But without loss of generality. So I have a central extension. And sometimes I will use, or in most of the times, I will use the extension by the degree derivation, D, but sometimes not. So my central element C acts as a scalar on all representations. The scalar I will denote by K, and I assume that this is not zero always. So we have a natural Z grading. Right, given by the degree of T. And the main definition a G hat module V is called smooth. If for some n, if for every element of V, for some n, GIV is 0, starting from this n. If you see this definition first time, you might think that it's very restrictive, right? So probably it's not difficult to describe such representations, and there should not be too many of them. So what are the examples? Yes. Yeah, so that's sort of a modern version. Of course, category O. Right, so these are smooth modules. Okay, Whittaker modules. Whittaker representations for G hat starting from some weight function defined on the positive part of G hat. Probably the best reference is the paper of Adamovich, Dražen Adamovich, Rensai Lu, and Kaimin Zhao. If I'm not mistaken, that's 2015 or 16. So they started the category of Whittaker modules, in particular simple Whittaker modules for affine SL2. And surprisingly, it's quite difficult to establish the reducibility criterion, and the way they did it, it's via the vertex theory for affine SL2. we have while modules. So we can start with a simple, let's say, weight. So I will always refer to a Cartan subalgebra here. It's a Cartan of G, and then extended by C and D. That's my Cartan subalgebra. And the weight structure is always with respect to this fixed Cartan subalgebra. G module, which means it's a weight simple module for Cartan H, right, and for G, and then C acts by a fixed scalar, and because degree derivation commutes with G, so we can define it by some fixed scalar. So if we want the action of D. And then we can construct the induced module from all the currents, so G tensor positive powers of T plus extended by the Cartan to G hat. Okay, so all positive currents we declare to be 0 on N, so it becomes a module over this part, over this Lie subalgebra, and then we induce up. So this module has a unique maximal submodule, and then I will denote by L and the unique irreducible quotient. So these letters, fancy letters M and L, give us a functor from G mod to G hat mod. And naturally, these are simple, smooth representations for G hat. Next example, so these are parabolic while modules. So let's consider the following triangle decomposition of G. I will write it like that, where this is the Levy subalgebra. So it's a reductive Lie subalgebra of G, and this is my parabolic subalgebra of G. So if L is just a Cartan, L contains Cartan subalgebra of G. If it is just a Cartan, this will be a Borel. And then we can lift it to a parabolic decomposition for G hat. So essentially that's the same as in this case, but we just put U in the positive part and U is the negative part. Right, so I will just write it as like that. Right, so it's a refinement of the decomposition here when we put just positive power of T in the positive part and negative power of T in the negative part. Now, this was my 0 part, right? And now I split it, and the radical U goes to positive part and U bar in the negative part. And now we can do the same thing. So take N to be a simple weight L module. And then we can construct induced module. And I will put here L to indicate that I'm inducing from an L module. That will be the same thing as before. Right, because if I have an L module, so I extend trivially with a trivial action of G hat 0, so then, or with a trivial action of U, it will be a G module. So there will be unique, also simple And this is like a generalized Verma module comparing to, both of them are generalized Verma modules comparing to the classical concept of a Verma module. Okay, so these are also, it's a family of smooth, simple smooth representations for affine algebras. And note that all these examples, they have finite dimensional weight spaces with respect to Cartan subalgebra. Right, so then we can naturally ask, what are the modules, simple modules in the Harishchandra category? So let's denote like that. The Harishchandra category, consisting of those modules that have a decomposition. So they're weight modules, and the dimensions of the mu are finite for all mu's. Now, all previous examples are of this kind. Then there is a theorem. It's an old result back in 2001 that says that if V is in this category, and remember that K is always non-zero here, it's simple, then V is isomorphic to a model that we described for some subalgebra L of G, a proper subalgebra, and for some cuspidal simple L module M. Cuspidality means equivalent, that any root element, not zero of course, X injective. And moreover, L is reductively subalgebra, right? So it has a semi-simple part. So all simple components of type A and C can be one piece of C and then several pieces of A, for example. Okay, so, but what it says that, I mean, all these models are smooth, and then it says that in the Harishchandra category there is nothing else. So all simple models in the Harishchandra category are smooth. Right, that's very good. And then, in other words, any simple smooth module with finite dimensional weight spaces is like that. So we have a classification. Well, we have a classification up to classification of n's. But this we also have, because there is another theorem of Matthew that tells us that if V is a cuspidal simple module, then V is a quotient of the following module. Okay, so L lambda clearly is the highest weight simple module with highest weight lambda. And here we have a composition of m functors. D alpha 1 x1, where alpha 1, alpha m are commuting roots. And xi's are some complex numbers. And these functors are called twisted localization. So let me describe now explicitly what it is. So first of all, we can take localization functor d alpha without x, because x will determine a twisting for us. So we consider, so alpha is a root. So let me define for g. I will do it for g for simplicity, and g hat is a similar, is done similarly. So let's alpha be a positive root. So we consider the generator f alpha, g minus alpha. And we consider a multiplicative set generated by this f alpha. And then we localize the enveloping algebra with respect to this multiplicative set. So I will just denote this like that. So it's a localization by f alpha, which means that we're inverting f alpha, right? That's what it essentially means. Then if we have a module over G, then we can localize it. So we can construct a module d alpha m. So it's a UG alpha tensor m over UG. So we get some module over the localized algebra. In particular, by restriction, it's a module over G. This is called localization of M. And we can, so if X is any number, then we can consider an automorphism of the enveloping algebra, which defined like that. And you see, it will be, because f alpha is adnilpotent, the sum is finite, and then we can define the action, a new action, twisted by this automorphism. And finally, what we get this module. Let's look at the example. So for SL2, so suppose I have generic lambda so this is my m lambda, right? So generically it's irreducible, so this is my f, this is my e. So I will do alpha is the only simple root that we have. Then d alpha m lambda will look like that. So I will have as before going to lambda. Then I continue from lambda plus 2. And I have a link here. So you can think this is my highest vector. And here now I have f inverse times highest vector. So this is a d alpha. Now, if I use x, if I twist the action, so I am building the bridge here. So if x is integer, nothing will happen. But if x is not integer, actually, this will be a non-trivial action. And at the end, I will get a string, SL2 string. Right, so this will be if x is not integer. That's how twisted localization works. So similarly, for g hat, we do the same. So here I take any real root, then everything is the same. Yeah, and we will get this twisted localization functor for g hat. So let me make a remark. Maybe first, d alpha x m lambda. I will be mostly use m lambda, and I will assume that this is a simple module, right? M lambda is irreducible, so lambda is generic. This module is simple for generic x. D alpha x m lambda belongs to the Harishchandra category if and only if alpha is a simple root. And third, so when we were talking about cuspidal modules, so it means that every root element acts injectively. So there are no kernels, which means if you pick a weight and you start acting by a Lie algebra, you get as far as you want in any direction, right? So the weight lattice of such module is the coset of H star by integers, right? And in such case, we say that the module is dense, where your weight lattice never breaks. These modules are not dense because they have a bounding hyperplane, but cuspidal ones don't. They are dense. So this module will be dense in this sense if and only if alpha, if the support of alpha is p hat. So it means that alpha has any simple root of our Lie algebra in the decomposition. It doesn't miss any simple root. If it misses a simple root, then there will be a bounding hyperplane. Right? For example, for this affine algebra, so you need to have, you will never get it, right? But if you have a more complicated linking diagram, so the imaginary root in this case has coordinates 1, 1, 2, 2, 1, 1, so you can take a real root 1, all ones. And if you do localization with respect to this root, you get a dense module. So we get lots of dense modules this way, in particular, and certainly alpha in this case is not simple, right? So then there will be infinite dimensional weight spaces. So we are not staying within the Harishchandra category. We go beyond, and this way we can obtain many new simple modules for affine algebras, and they're all smooth, right? It shows actually the complexity of the classification problem of smooth modules. Yeah, and I should say we don't know even for SL2 hat, it's still an open problem. This is one of the main tools of constructing them. But the problem is still open. And I want to introduce a T functor, or T alpha functor. So if we do, before twisting by X, right, if we look at this module, it has M as a submodule. So it's never simple. Right? So let me define T alpha M, or maybe M lambda, since this is my main interest. So I will define it as a D alpha M lambda, quotienting M lambda. Okay, so instead of running back and forth, I'm not supposed to do that. So let me look at the SL2 case. So this was M lambda. Then we got this module as a D alpha, and it has M lambda as a submodule. So when we take a quotient, we get this module. Right? So we go from highest weight to lowest weight. Of course, we could twist the action and get back to category O, and that's Arkhipov functor. But I don't do that, right? Because remember, mainly I will use alpha, which is not simple. Then I don't care. I will never go back to category O because I will get infinite dimensional weight spaces and the dense moduli. So for SL3, for example, let's look at SL3, what happens. So we start from this module, and then we will get this module. Yeah, this is T alpha M lambda. That looks like that. And then remark. Suppose so we're assuming M lambda is irreducible, so it's a Wakimoto module. So I can consider Wakimoto realization for M lambda. Then I can assume that my space is something like that. Delta x0, then x1, so on. And then tensor with y's. This is the space for Wakimoto module. And in this realization, Fn, right, which is F tensor Tn, x like minus delta xn. So if I choose, and my roots are plus minus for SL2 hat, like that. Real roots. So these are real roots. Alpha is a root of S, just SL2. So x0 corresponds to f0, right? And the root alpha. So if I do localization for alpha, then it means I'm changing delta x0 to x0 in this realization. So then the Wakimoto type representation for T alpha will be delta x minus 2, delta x minus 1, and then here x1, x0. Now, what if I do T minus alpha plus delta? This positive root. Then I can apply it here, but then I will switch this one. You see, then it will be, and of course, tensor y's, right? Y's are always there. So it will be delta x minus 2, then x minus 1, x0, and so on, and tensor y's. And you see, so this is again a type of Wakimoto model. So it's a similar situation as what we had here for SL3. In the affine level, it happens. It's the same thing. So this is just the highest weight model with respect to a new Borel, different Borel. And we can continue. Now we can do this route and so on. And this is called, physicists call it spectral flow, right? Which just corresponds to application of certain automorphism, essentially while group to our representation. But what if we start here and we don't do it step by step, but I want to do this one, which means I'm considering directly minus alpha plus 2 delta. This is the root that corresponds to this. Then I will change x minus 2. I will switch to x minus 2. And I will get this space as my supporting space for representation. And this is not classical Wakimoto type or spectral flow of Wakimoto. This is something new because it will be dense. Now, this is no longer, this is a simple root, and this is a simple root. But this fellow is not simple anymore. So we will get a completely new module, but in fact, we can write free field realization for this representation, even though it looks wild. So this is quite an interesting functor. It has also the following feature. And again, every time we get a simple smooth module. Well, so we have, so maybe property, maybe theorem. So there is one already published and one that's supposed to appear maybe by the end of the month in the archive. So we know when these modules are simple for any alpha. To save time, I will not write the conditions. And the second one is quite interesting. See, we have a root alpha. So we have a Casimir. This root alpha determines, no matter if it's simple or not, determines SL2 subalgebra. So let's look at the Casimir of the corresponding SL2 triple. And then let's consider gamma alpha, a subalgebra generated by C alpha and Cartan. Then T alpha M lambda is gamma alpha finite. Which means two things. First of all, gamma alpha has a spectrum, right? So we can decompose T alpha M lambda into eigensubspaces of gamma alpha, generalized eigensubspaces of gamma alpha in general, and the dimension of each subspace is finite, even though the weight subspaces are infinite. See, with respect to just Cartan, the weight subspaces are infinite, but this every big infinite subspace we can decompose with respect to C alpha, and then they break up into finite dimensional ones. Which is very interesting if you think even for G, not affine, even for G, this is quite interesting because it means that any commutative subalgebra that contains C alpha is finite on these representations, has a decomposition into eigensubspaces, which are finite dimensional. This is an analog of Gelfand-Zetlin representations for type A. But in fact, now you can take any maximal commutative subalgebra for any, in the enveloping algebra of any Lie algebra, not necessarily a cell. And as long as it contains C alpha, then we get this category, which is quite similar to Gelfand-Settling category. Okay, and so next point, generalized Whittaker. Generalized Whittaker modules. So we can play the following game. So for SL2 hat, so G is SL2. Let's take a pair of integers, Mn. With such restriction. And then we define a subalgebra, let's call it S and M in G, generated by, so I will take all HK, so this index means H times tensor TK. And then I will take ES with S greater than N, and FT, no, T is not good, maybe FR with R greater than M. So I generate a subalgebra by this element. So of course, also I have C, but I will not take D in this case, no D. And now I take a function phi and M, a homomorphism to C. And I construct this generalized or partial Whittaker model, just inducing from the character. So let's denote by M, pi, and M. That's induced model. From one-dimensional space. So this is a family of non-weight, because we don't have D action, but weight with respect to the finite dimensional Cartan. Kx, I will assume that phi and M of C is K. And theorem. S, yeah, oh, sorry. So this is our result with Xinchen Guo, Hui Shuo, and Kaimin Zhao. So this module is a simple weight, but no D. Smooth module if and only if. We have this decomposition, and It's a non-critical level. So we get a huge family of such Whittaker type smooth simple modules. This generalizing the result of that I mentioned before for Adamovich, Liu, and Zhao when they consider just classical Whittaker modules. So their family is a particular case of this. If level is critical, if k is -2, then there will be a submodule, but we know exactly what are the singular vectors and what is the maximal submodule, and we know the irreducible quotient. And from here, you can produce actually representations for the full affine with T, just tensoring. If you tensor our module with CD, then we get a representation of the full affine, and it's not simple. What we need to do, we need to kill the Casimir, affine Casimir element. So if we kill ideal, well, killing the Casimir or defining the action of the Casimir element as a scalar, we get a simple representation. Check the time. Let's have 1 minute, 2 minutes. Okay, so in 1 minute, I want just to, I did not start with the motivation. Why should we care about smooth representation, right? So it's kind of natural condition, but why is it interesting? So if we look at these representations, right, that I defined in the beginning when our module n over g, finite dimension g is just trivial, then these have additional structure of vertex algebras. Which are relevant to conformal field theory. And so then this one, let me call it Vk, and this is Lk. And then it is important to understand the irreducible representations of these vertex algebras. So Vk mod is the same as G hat smooth. In particular, from what I described, we have a classification of all irreducible Harish-Chandra representations of this vertex algebra. The more delicate question is Harish-Chandra category for Lk. So let me just denote it like that. So this corresponds to certain representations, or certain smooth representations of G hat. And it's not, there's no general theory that gives the complete answer. It always depends on K. So for example, for K integer, positive integer, that's an easy case. Simple modules are just integrable modules. That's an easy case. If K is rational, so-called admissible level, that's where the study is going on. And then the answer is known for highest weight modules. That goes back to Katz-Wakimoto. And then the modern point of view is Arakawa. Classification of for all admissible levels is known. So admissible level looks like that, with some restrictions on P and Q. For SL2 affine, this was done by Adamovich, Milosh. For SL3, So it was done by Arakawa and Ramirez. And for general case, the general case, classification is given by algorithm. So there is an algorithm due to Kawasetsu and Rideau. And the modules in this category, they are naturally they are not dense, right? They all have hyperplanes. That's why you can do it. And they're called relaxed highest weight representations. Yeah, that's what physicists use today. But essentially, they are just generalized quotients of generalized Verma modules. And again, the main tools are those functors that I define, D and T, and that's how manipulating with those functors actually you can build, and following the idea of the Matthew theorem, you can get all of them in this category. But what's going on beyond, the only examples that we know so far are those that I presented. So in weight category, they're just images of D functors and T functors. And in non-weight categories, they are these generalized Whittaker representations. Thank you very much.
Thank you for a nice talk. Any comments, questions? I have a question. What is known about the characters of these models? Can you compute them?
You mean?
Yeah.
But as you can choose any function as long as this value is not 0. Yeah, you can choose many of them.
No, the character of the module M.
Oh, the character of the... No, this one, no.
Is anything expected from them?
Because you see, there is no D. So the spaces, the weight spaces are huge.
Okay. So there are no some kind of analogs of characters?
No. Where we expect to have maybe here, because there is some finiteness.
Okay.
You see, there is a gamma alpha finite. There, we have a notion of a character. This is ongoing.
Okay.
Yeah, but there, yes.
So, any other questions?
Do you expect some sort of Kazan-Lustig relation between these fine algebras and quantum groups?
Well, because there are, you can see there are too many, right, of smooth simple modules. So there's a new approach trying to establish some equivalence of categories. Like for SL2 hat, there is equivalence with representations of small quantum group. So it is expected that it can be enlarged, but it's really only this one, only this category. Yeah. Right. Yeah.
Okay. More questions? Nope. So if there are no questions, thank you again.